In this video, we're going to explain how floating point numbers are added. We have a different video on multiplying floats, and it might be a good idea to view that one first because it addresses many of the general issues involved in doing arithmetic on floats. As in that video, we'll be focusing on normalized floats. Denormalized floats are handled similarly. Infinities and nands are handled specially. We'll assume that you're already somewhat familiar with normalized floating point numbers and their representations. Again, we have a separate video on that topic, and we'll review it here only to the extent necessary to make our current topic intelligible. For this video, we'll be assuming 32-bit floats, but everything we say can be applied with some minor modifications to 64-bit doubles. Recall that floating point numbers are effectively a variant of binary scientific notation. That is, numbers of the standard form shown here. There's a sign, plus or minus, and a real number constant c in its specific format, times some integral power of 2. For normalized numbers, c always has a single 1 to the left of the binary point. In floating point format, numbers are stored in 3 fields: sign, exponent, and constant. The constant field is sometimes called the frac, mantissa, significand, or coefficient. For 32-bit floats, we allocate 1 bit for the sign, 8 bits for the exponent, and the remaining 23 bits for the constant. Recall finally that, for normalized floats, the exponent is stored in biased form, meaning that the range of possible exponents, minus 126 to positive 127, is shifted in the positive direction by adding a constant of 127. This ensures that the value recorded in the exponent field will always be positive. To recover the actual exponent, we just subtract the bias of 127. Understanding addition for floats really is easiest if you think of them as just an alternative format for scientific notation. So let's consider how one adds numbers in scientific notation. Let's start with decimal, since it's most familiar. Suppose we want to add the 2 numbers shown here in scientific notation. That is, we want to compute this sum. Here we're adding 2 positive numbers, so the result will be positive. But unlike multiplication, if the signs of the add-ins differ, it's not always obvious what the sign of the sum will be. It depends on their magnitude. The fundamental reality of adding 2 numbers in scientific notation is this: the addition can only occur if the exponents are identical. Unless that's true initially, then one of the 2 numbers must be adjusted to make it true. For example, our 2 add-ins have exponent 2 and 4 respectively. We have to adjust one of these so that the exponents are equal. This can be done with either add-in. There's no strong reason to choose one over the other. This process of adjusting the exponent takes that add-in out of proper scientific notation, but that's a cost we'll have to bear, at least temporarily. Let's choose the multiplier of 10 to the 4th, adjusting it down to 10 squared to match the other add-in. Since we're decreasing 10 to the 4th by a factor of 100, we have to compensate by increasing the coefficient by a factor of 100. That means moving the decimal point to the right by 2 places. That yields the number shown here. Now we have 2 add-ins with the same exponent. Using the commutative and associative laws, and factoring out the common term, we have the expression shown here. Now we can add the coefficients. We're almost done. Our result is correct, but it's not in the appropriate format for scientific notation, that is, with exactly 1 digit to the left of the decimal point. So we move our decimal point 2 places to the left and compensate by increasing the exponent by 2. It might also be necessary at this point to round the coefficient if it has too many digits to the right of the decimal point. Now let's perform a similar computation in binary. Imagine we're adding the numbers in binary scientific notation shown here. As in the decimal case, we have to adjust the exponent of one of these so that they'll match. Let's adjust the factor of 2 to the 6th down to 2 cubed. We compensate by moving the binary point in the coefficient 3 places to the right, which gives us this number. Notice that it's no longer in proper scientific notation, but that's necessary here. Now that the exponents match, we can add the two numbers together. Again, we factor out the 2 cubed and add the coefficients. This yields this sum. Once again, the answer is correct, but it's not in the right format. We want to have a single 1 to the left of the binary point. So we adjust the coefficient by moving the binary point 3 places to the left and compensate by raising the exponent by 3. That result is shown here. Finally, this result is easily converted into floating point format. So far, we've explained addition of floating point numbers by doing the addition in the equivalent scientific notation. An obvious question is this: why not just do the addition directly using float notation? That's certainly what the computer does. Let's think about how that would work. Let's look at our two binary add-ins again. In float notation, these are as shown here. To add these together, we'd perform the following steps. First, note that the exponent fields don't match, so choose one of the numbers to adjust. That means putting it into non-standard form, with exponent matching the other number. This requires adjusting both exponent and coefficient, and can't be done within the float format. Second, compute the sum of the mantisses, remembering that the add-in we didn't adjust has an implied 1 in front of the binary point. Third, the exponent of the sum is simply the common exponent. Finally, if the result is not in appropriate format, we'd have to adjust the exponent and mantissa again to put it into appropriate form. This may also involve rounding the mantissa. That's not too hard on paper, but there are some significant complications that make a floating point adder a pretty complex piece of circuitry. For one thing, each mantissa is stored with 24 bits of precision, but the sum of two 24-bit numbers may require 25 bits to store. And actually, it's worse than that, since in adjusting one of the exponents, we may have shifted the binary point for that number several positions to the left or right. The hardware would actually have to store many more than 25 bits of precision to do this computation accurately. Also, the sum likely will not be in the right form for a float, that is, with exactly 1 1 to the left of the binary point. In that case, the result has to be adjusted, affecting both the exponent and mantissa fields. This has to be done after rounding the mantissa, since rounding can also yield an improper format. There are additional complications if one or both of the add-ins is a denormalized number or special value, or if the result is too large to store. The hardware must deal with these corner cases also. It's certainly possible to do all this. Floating point hardware does it flawlessly. But most humans aren't very good at it. So when adding two floating point numbers, it's typically easier for us to extract the numbers into scientific notation, perform the addition there, and then put the result back into float format. This requires some care, but it's a lot easier than trying to mimic the hardware.